Up to this point, we've dealt with integrals that are completely indefinite. We're not even concerned with, we're looking for expressions for the area under the curve, so to speak. Or they've been definite, they've been from one particular point to another. But now we'll be considering functions whose graphs maybe look something like this, where this edge of the graph never actually gets to the x-axis, or in a sense there's always some space between the graph itself and the x-axis. There's no boundary. And we'll be looking at when there's actually an area you can calculate. And strangely enough, sometimes there is an area you can calculate and sometimes there isn't. So these kinds of integrals, improper integrals, have the form an integral from some finite number to infinity of f of x dx, or they begin from negative infinity and go to some finite number, or the limits of integration are completely unbounded. So we're going to consider those scenarios. And ultimately, for all of these, the issue is one of limits. Do these integrals have a limit or not? And if they do have a limit, then the integral is said to converge. If it doesn't have a limit, then the integral diverges and we're kind of stuck. So let's begin by way of example, and we'll consider the integral from 2 to infinity of 1 over x cubed dx. Now take a moment and graph that just so you can see what it is that we're thinking about. Right, so graphically, we are looking at, we're only focusing on the first quadrant because we're starting at 2. And we're looking at something whose graph in the first quadrant does something like this. And we're really focusing here, right, from 1/8 as a high down. Is there a way for us to make sense of this space here or not? Well, in order to do that, what we want to know is, what's the limit, we'll say, as b goes to infinity, of the integral from 2 to b. And it's very important to note that since we're dealing with the limit process, you must write the limit as b goes to infinity down. And you must continue to write it until you actually take the limit of some expression. Now I have this definite integral from 2 to b, and so I'm still dealing with the limit as b goes to infinity. The integral of 1 over x cubed, well, let's see, that's going to be, it would have been x to the negative 2, so this should be negative 1/2 x to the negative 2 from 2 to b. I'm going to clean this up for substitution purposes. So this is the limit as b goes to infinity of negative 1 over 2x squared from 2 to b. When I substitute b into this, I have the expression negative 1 over 2b squared minus, when I substitute 2 into this, I get negative 1 over 8 and now this is an expression where I can take the limit of this, as b goes to infinity, this entire denominator is getting massive. The limit of this then is 0. So this becomes 0 plus 1/8. So this converges, and the integral's value is 1/8. Because the limit of this exists, the limit is of the expression involving b is 0. I can actually continue forward, and the value of the integral is 1/8. That's the area under that curve. Even though it's always getting closer and closer to the x-axis and it never reaches it, it does converge. It is the kind of thing that converges, and its area can be found.